So I'm going to briefly talk about Shell's FCC technology and all the tools we have been using for troubleshooting and doing the optimization work for our asset and also for our licensing customers. And after that, I'm going to dive into 3 different cases. There are some examples and how we are using the computational methods to help us improve some of the designs or help the asset support. Okay. So Shell is an operator, and even though Shell has divested a lot of refineries in the past few years, but we still have a few number of refineries left in the world, and also we are a licensor, and we license our technologies to customers, third parties. We have a over 70 years R&D program, and we have over 30 grassroots designs, 150 revamped units, 80 TSS units. And talking about the TSS, so Shell is actually the inventor of the TSS concept, and we still occupy a good number of market share. As an operator, so we have exceptional operational experience, and all those failures and experience we learned in the past are all embedded into our Shell designs. So we provide technical support, diagnosis, and through TSA to our customers and third parties. And Shell has some very unique hardware designs, like the feed nozzle, cyclone designs, strippers, span catalyst distributor, TSS. We also have a kinetic model, the Shark process modeling, and we also license that software to our customers. Some other stuff like CFD, we also have data science, AI capabilities, and all those are embedded into our unit operation and embedded into our process development. Shell also have a full-scale pilot plant, and we do catalyst selections, assessment, and also we have a feed nozzle testing. And also we have a feed nozzle testing rig, so that is like a full-scale 6-inch nozzle, water cannon, and we can change the feed nozzle tape. And so you can do all kinds like a PRV, capture just the droplet size and do ligament testing. And yeah, we also offer trainings to our customers, FCC courses and storm training to the operators. So, and that's all for the licensing talk. So let's dive into the case studies. And the first one is asset support example we had. And this is a refinery in the Gulf Coast area. So this refinery has a very unique setting configuration. So it got 2 separate risers. Each of the risers fit into a primary cyclone, and each of the primary cyclone divides into 4 external secondary cyclones. And so after the secondary cyclones, it got some tilted deep legs, and that is have a certain angle from the vertical side. So basically, there along the deep legs, there are some purging nozzles. So the aim is to provide the aerations and to keep the path clear, and also provide some fluidization for the lower side section of the deep leg. So the deep leg is coming back into the primary cyclone. So in 2021, we got a deep leg leak, and it's on one of the secondary cyclones. So we did this inspection. We use an infrared camera to do the inspection on the site, and we found this thermal gradient. So the leakage location is here. This is a flange, and we got a purging nozzle here, and it's purging steam into the system. And the leak happens on the well location here. So, but as you can see from this infrared camera inspection, so it has a thermal gradient here. And at the time, we were thinking, oh, this is thermal gradient and cause the thermal stress, and thermal stress cause thermal fatigue on the metals. So that leads to, over time, that leads to the crack of the deep leg. So we also did inspections on some other deep legs, and we also found similar issues, but those are cracks. They didn't lead into the leakage. We also consider some other stuff like the piping integrity, but the piping is good enough mechanically to handle this temperature of the process. The process temperature is something like 900 Fahrenheit, and the steam should be 500 Fahrenheit. But in reality, they couldn't keep up the temperature, so the temperature is actually 400 something. So for the CFD simulation, so objective is to understand the impacts of the catalyst flow and also what could be happening, and if we change some conditions, process conditions, what could be happening at the location, and what we can do to mitigate these thermal gradient issues. And so on the left side this is just an animation from the CFD and to show the thermal gradient. And as you can see, this thermal gradient is cycling, and this line that is the well location, that is the crack location. At first, when we were modeling this system, we were thinking about modeling the whole system, like the cyclone body and also the deep lag, model everything. But that is very computationally expensive. So this location is actually 30 feet from the cyclone body, and also 4 feet, around 4 or 5 feet from the exit of the deep lag. And we did another simulation, so with the help from CPFD, and we did for another project. So that one is a cyclone modeling. That one took 2 weeks to run, and it was something like 5 million cells. So at the time for this one and the asset, they want the answers fast, and so basically we end up with only modeling a section of the pipe. So if you are only modeling a section of the pipe, the boundary condition becomes very important, because the boundary condition is going to impact how the thermal gradient flows. And we tried over 40 different boundary conditions, and this is the best we can get from this simulation. And so we did some parametric studies in trying to provide the site some short-term solutions. And that actually raises a lot more questions. So let's first take a look at the parametric study. So these are just some slides from our package to the customer. So this does not conclude everything. But we did a parametric study on the deep lag, and basically what we do is we change the mass flow rate coming into the purging nozzle. So we are changing the mass flow rate, and so you can have more flow or less flow. And on the y-axis, that is basically the distance over the deep lag. That is a cracking distance. On the x-axis, that is a temperature differential. So as you can see here, when you increase the mass flow rate, so 100% means that is the current configuration, and you can decrease it to 75, 50. But generally, if you increase the mass flow rate of the steam into the system, the thermal gradient is going to become more severe. And that also makes sense because the steam is cooler. We also did some nozzle angle study. And the reason for this study is that, so before the last turnaround, like 5 years ago, they were using a 90-degree nozzle angle to purge the deep lag. And during the last turnaround, they changed it to 45. And after that, so before they make the change, there was never a deep lag cracking issue. So after they make the change, and they saw a thermal gradient, and also they have the crack issue happening. So we did a CFD simulation for the 90-degree, and this is what it looks like. So the thermal gradient doesn't reach the flange location. So that means from CFD, at least from CFD point of view, and if you change it back to 90, and this thermal gradient issue can be solved. But the reason why they changed it from 90 to 45 is because at the time they found some pluggage, and because if you have deep lag and you have 90-degree, and that is easy for the catalyst to ingress into the purging nozzle. That was the reason why they make the change to 45. So at the time, we learned this parametric study, and we provide a short-term solution to ask them to reduce the mass flow rate into the system. And so that didn't happen. The reason is that they use the orifice to control the flow coming into the purging nozzle, and they have to do a MOC and to make the changes, but some other stuff got in the way, and so that never happened. So 1 year later, and in 2022, they have another leakage at a similar location. So they have 8 deep legs, and basically it's like a north, south, west, and east. So they got a very similar location and got the leakage happen again. And so the second time, when we saw that leakage, and we were asking some questions, why this repeated leakage and fail in certain locations. And because this is a repeated leakage, so that got attention from the upper management in Shell, and they urged us to do more safety simulations. That's good. So we were thinking about looking at the drawings, and we found something that is very interesting. And this kind of thing is maybe a lot of times be ignored by the mechanical people. That is, when you have a deep leg, like for example, this is a deep leg and it's tilted in an angle, and you have, for example, this is a purging nozzle, and even though it's 45 degrees to the deep leg, actually, it has a freedom in the radial direction. So you can put the nozzle everywhere. For example, you can, and also, when you have a tilted deep leg, so basically the catalyst is also always, most of the catalyst is going to flow in the lower section of the deep leg. So basically, if you put your purge nozzle here, it's similar to the most left picture, and that means the purging nozzle is going to be submerged in the catalyst flow. And so this is a result from Barracuda software, by the way. And if you put it away from the catalyst flow, so it's going to be something like a half merged, half submerged, and half exposed to the vapor, gas vapor. And also you can put it totally away from the catalyst flow. And the results is astonishing. So as you can see, in 2021, so when we were doing the simulation, basically we assume all the angles of the radial angles of the nozzle is perfect. It's perfectly submerged. So this is the result of 2021 simulation. But when we change the radial angle to some different angles, so you can see the thermal gradient worse. And also the cycling behavior is more severe. And also, if you put it away from the catalyst flow, and the vapor is going to lift this purging flow up. So we did this safety simulation, and then we did a field walk. And so we climbed the tower, and we look at how they are installed. And not to our surprise, they are not perfectly installed under the catalyst flow. So even though the 45 angle is always kept, but it's like they put it randomly because some piping, some of the piping obstructions, and they have to put some nozzles in a certain angle away from the catalyst flow. So we did all this, and we proposed some recommendations to the site, and they are going to implement those changes in it's a coming up turnaround. And right now the unit is operation fine. And also we did another safety simulation we didn't show here. Is basically to change the purging media to another media. And that also helps because when you operate with a low temperature steam, that is going to has a tendency to form some droplets in your dip lag, and that is going to cause a cement-like material, and that could plug your nozzle. And the impact is, you could see different kind of like the impact because when you have a pluggage, and basically the velocity of the flow is increased, and based on the jet penetration, different angles, you could worsen the thermal gradient at the location, or you could maybe lessen the thermal gradient at the location. So that is the first case. So the first case is basically for the asset support, and we have a second case. This case is actually very similar to what Peter showed yesterday on the Chevron's regenerator. So basically, this is one of our customers, and they have a regenerator. Oh, sorry, they have a regenerator setup, and this is a small regenerator. It's only like 20 feet wide diameter regenerator, and so basically they have some issues with local afterburn in the dilute phase, and the reason is maybe they don't have a even catalyst distribution that is going to cause your air uniformity in the dilute phase. And spin catalyst distributor is basically to spread the coke-laden catalyst into your system, and it's very important for improve the air utilization, reduce NOx, and also reduce local afterburn. At the time when we were modeling this stuff, so there are multiple constraints we have. The first one is the unit is very small, so you don't have much space to work with in the first place. And also, all these air grade cyclones, and they do not intend to make the changes to those things, and those are also increase the difficulty of the space limit. And also they got a withdrawal well here, so you have to put your standpipe a certain distance away from the withdrawal well here. You don't want your catalyst to directly go back into the riser. So basically we did a safety simulation, and because of the time limit, so basically the customer wanted us to give them the safety results in 1 month time. And so we did this cold flow model, and this is their benchmark, their current existing design. And they have a small standpipe, and this is just an open pipe, spin catalyst distributor, just open pipe into this vessel. As you can see, this is an animation, and it's causing this kind of like a circulation, because the catalyst is basically flowing into roughly the center of the vessel. So it causes this circulation, and on the right side is also having some circulations. So basically the gas found an easy path to rise through the center, and that is not good for your air uniformity in the dilute phase. And also we have some streamline pictures to show that. So at the time, we proposed multiple different options, and with the limit of the space, so we did an extended pipe, we do different side windows, and we also reorienting the pipe. And basically, we look at the catalyst distributions in the system, and different design, they are going to show you different kind of like behavior, catalyst distribution, standard deviations, catalyst uniformity in the system, and also the air uniformity. So I only show some examples of the slides here. So this is not everything. And also, when you look at all those, you can come up with a better design. And so this is very similar to the Chevron's case, so I'm not going to spend a whole lot of time here. So in summary, this safety can help with your design optimization. Yeah. So the last case, so I remember in yesterday's meeting, and we were talking about decarbonization of the industry, how to make FCC more efficient. So one of the solutions is co-processing. And I remember yesterday some operators were mentioning, so let me show the next slide. So some refiners are mentioning they have some difficulties of co-processing the biogenic feed, like biopyrolysis oil, cellulose, coconut oil, whatever, those bio oils. So they have some difficulties because they are using a conventional feed nozzle. And all these materials, they are very heat sensitive. So basically, they are going to degrade at a higher temperature. The riser is like 900 Fahrenheit. And depending on the location you put in the put your bio stuff in there, it could be like a 1200 Fahrenheit if it's close to the regenerated standpipe, catalyst standpipe. So because of the high temperature and the biogenic source feedstock may degrade, and that is going to create coke and plug your feed nozzle. And also it can prematurely vaporize, and that is going to create a higher pressure drop in your feed nozzle. So in Shell, we developed a new technology, and that is a co-processing nozzle, and that was patented last year. So that is basically we use some special metallurgies. So that metallurgies is going to help to prevent the heat from the riser from coming into the internals of the nozzle. And so we are able to process a wide range of feedstocks that cat cracker can handle, all kinds of like a biogenic, and also the biogenic material is very tough because it has some contaminants. It can cause corrosion problems to your feed nozzles. And we also have the metallurgies to solve those problems. And we did the FEA analysis on that co-processing nozzle, and so basically on the outside is the riser temperature, and you can see, so internally, for example, you put in the feed like 100 Fahrenheit, 120 Fahrenheit, it's going to stay at that temperature when you put it into the riser. And also we did so this is actually a test after we fabricate the co-processing nozzle. So we already have 2 co-processing nozzles installed in 2 of the Shell's refineries, and we are planning to install 1 more in Shell's another refinery in the upcoming turnaround. And this is a test result. And this, so basically after we fabricate the nozzle, and we put a thermal blanket over the nozzle. And then make sure the outside temperature is always 500 Fahrenheit. And this is the temperature, and these are actually the locations in the internal of the feed nozzle. And we put some thermocouples there to monitor the temperatures. And this is before we put in the water. We use water and air to do the test. This is before we put in the water. The temperature is super high, but after we put in the water, so the metallurgies of this nozzle did a great job. So the water temperature is something like a 60 Fahrenheit, and it stays at 60 Fahrenheit when you push the water in there. We also did safety study on this thing. So we have multiple designs. So one of the design is we put this co-processing nozzle inside an emergency steam nozzle. So if you think about it, so when you put this in a steam nozzle, the steam temperature is going to provide a further protection because the steam temperature is much lower than the riser temperature. But that causes another problem because the co-processing nozzle, and if you are the licensor and you know that, you have to keep a certain velocity at the nozzle tip to have a full atomization. And that velocity is very high comparing to the steam velocity. And I can't tell you the number, but it's a magnitude different. That is going to cause some problem because when you have 2 flows that is very close to each other, so that is going to cause a differential pressure. That is going to pull the steam into your co-processing feed. And in the operation, that causes a problem that you design your steam nozzle maybe at a certain velocity, and because of the differential pressure, that could cause some velocity drop at the side of the wall of the steam nozzle. And basically what we did, we did an atomization model. We used both Fluent and Barracuda. and also, so I think we contributed to a feature add-on to Barracuda, because at the time we were using the solid to model, basically solid particles to model the bio-oil, but later Barracuda come up with a new version, and that is able to treat the solids as liquids. So we use that, and we update all our CFD models. Our goal is basically to make sure so the steam have good enough velocity to come out. And there are some other problems because of differential pressure, that is eddies. So if you are a licensor, you don't like the word eddies. These pictures are good CFD. These are CFD results of some good designs. We also have a lot of different geometries that is going to cause a lot of eddies inside of this nozzle. And so basically we ditch all those designs. So CFD is great in help you solving this kind of when you change some geometries and you can see what happens. This is a picture of when we were doing the test in the field after the coprocessing nozzle is fabricated. And also Shell licensed all these coprocessing nozzles to third parties and customers. And also our coprocessing nozzle, because of the location of the installation, and it's not going to interfere with your current feed nozzle. You can read this. And oh, by the way, we also have some other technologies. And yesterday we were talking about direct air capture. And so actually in terms of carbon capture, so there are 3 technologies. Amine-based material is one thing. That is pretty mature technology, and Shell has a cancer of solution for that one. Direct carbon capture, so I think Exxon, Chevron, and we are all working on those. There is another thing, so and we are working on the design. So that is basically use a solid-like material. And you use a fluidized bed, and that solid-like material can absorb and dissolve CO2 in a large quantity. And also, that design of the catalyst can also be able to handle a lot of contaminants that your amine cannot solve. We are going to patent that design, so we didn't show anything here. But CFD actually play an important role in designing that system. It's very similar to a fluidized bed, but it got some internals that differs from a normal regenerator or normal reactor. You can also read this. And so basically, that's all my presentation. And thank you for listening. And I open the floor for questions.